So, this is the nth order arithmetic sequence formula and the nth order arithmetic sequence sum formula, where big N corresponds to the arithmetic sequence order, T corresponds to the first term of each layer nominated by I, starting from the top, and small n corresponds to which term in the sequence you want to calculate or calculate to. But why? Why does it so happen to be the binomial coefficient? Let me explain. I am going to use a third order arithmetic sequence with 7 terms to explain it. When we see this, what is actually happening? It is just the first term of each layer being added to each term in the layer above it, where each term in the layer are also being added to each term in the layer above it, and so on. If we look close enough, the only thing playing a role here are the first term of each layer and the length of the graph. So I am going to strip barren this graph of its subscripts and really show what's happening. Let's start with the obvious. Every layer has the same term, specifically the first term of that specific layer. This is to visualize that the first term always persists throughout its next iteration in that specific layer. Next, to visualize the additions. Focus on the bottom layer. What happens to D when it gets added to the layer above it? Our first D gets added to the second C in the layer above it, which then moves to the next term, where it then gets added with another D, and so on and so on. This applies to all layers in general. If we focus on the individual Ds, we see that the first D exists on the C layer from the second C and so on. The second D exists on the layer from the third C and so on. The third D exists from the fourth C and so on and so on. Knowing this, instead of drawing an arrow from D to just the term above it, let's draw arrows from a D to all terms in the layer above it that it exists on, so that we know precisely how many D's is in a specific C term. Now, we can see that the second C term has one D term, the third C term has two D terms, the fourth C term has three D terms, and so on. To see how many D terms exist in individual B terms, we can repeat this process again. To count how many D terms exist in individual B terms should now be the matter of counting all combinations of arrows originating from a D term to a B term. For example, there's only one D term in the third B term, three D terms in the fourth B term, six D terms in the fifth B term, and 10 D terms in the sixth B term. If we were to find the sum of the B terms from the first term to the sixth term, the amount of D terms contained in that sum will be the sum of all the D terms we just got. That is 1 plus 3 plus 6 plus 10, which is equal to 20. If we want to find the seventh A term instead, the amount of D terms contained in that term will also be 20, because to get a term, we add the first term with the sum of the sequence below it. So, it seems that to get the total amount of D terms in either the B term sum or the seventh A term is this thing. This set of arrows describes the addition of the D terms through the layers and represents the amount of the D terms that exists. This representation can also be applied to the other layers. Let's call this representation for the structure from now on, so that we can refer back to it easily. Since this structure corresponds to the total amount of first terms that exists in a sum or a term, it corresponds to the binomial coefficients that we found in our formula. So, to calculate a term or the sum of an arithmetic sequence, one must count every possible combinations of the structure for a specific layer, multiplied by the first term of that layer, do that for every single layer, and add the result. But why exactly does the structure correspond to the binomial coefficients we found in our formula? Let's visualize everything in a more simple manner, as notes and arrows. This is a three-layer graph and all possible paths visualized. Let's take a look at the definition of a binomial coefficient and compare both of these. Here, On the left is the three-layer graph, and on the right, the binomial coefficient definition. The amount of all possible paths there is on this graph corresponds to the numerator in the binomial coefficient. Multiplying the amount of nodes in each layer with each other describes all possible paths that there are. Then, the denominator divides the graph in such a way that it results in the structure. We can observe that the denominator is the same no matter the length of the graph, since it holds no n. So, if we rearrange the expression into this, we can see that the ratio between the structure and the graph is always the same no matter the length. In our case, 1/6 of the whole graph is the structure. My guess is that the denominator slash ratio is correlated to the amount of layers. Let's try proving that the ratio will indeed hold no matter the length of the graph. The end objective here is to show that the structure really is the binomial coefficient found in the formula and to prove that it is. Let's start with the most simple graph that there is, a single node. The ratio between the structure and the whole graph is 1. We may extend this as long as we can, and that ratio will still hold. It is like the bottommost layer in every graph that we have seen. The structure starts from every node at the bottom. Next, two-layer graph. Let's start with the base case, the most simple two-layer graph. It is very clearly visible what is going on here. There are only two paths, and the structure here corresponds to this singular path. Now we extend the graph to the right. Now the graph gains additional paths, and the structure too. The structure now looks like this. It is obvious that the ratio is 2, but we need to prove this. Considering that this graph contains the previous graph that also holds that ratio, the only way the structure can keep this ratio is for the additional paths and the structure within it to have the same ratio as well. Since the additional paths must connect to at least one of the new nodes, the paths can be divided into two groups, the ones that connects with the top right node and the ones that connects from the bottom right node. The amount of group is correlated to the amount of layers. Since only the first group have arrows going to the right, it is the group that is a part of the structure. We have selected a half of the additional paths. Therefore, it retains the ratio, and therefore, so does the whole graph. Now, we can extend the graph once more. The reasoning from before is used here again. In order for this graph to retain a ratio, considering that the previous iteration holds that ratio, the additional paths and the structure inside of it must hold that ratio as well. Since the additional paths must connect to at least one of the new nodes, the paths can be divided into two groups, the ones that connects with the top right node and the ones that connects from the bottom right node. The amount of group is correlated to the amount of layers. Since only the first group have arrows going to the right, it is the group that is a part of the structure. We have selected a half of the additional paths. Therefore, it retains the ratio, and therefore, so does the whole graph. This reasoning can always be applied to the next iteration of the graph, if the iteration before it holds the ratio, hence making every iteration thereafter true, as long as we have a base case, an iteration that is proven to be true, which we have. So, we have proven that the ratio, that being 2, between a two-layer graph and the structure will always be the same no matter the length of the graph. We covered two-layer graphs. Now we go into three-layer graphs. Let's start it by having a base case. The structure here looks like this. The ratio between the graph and the structure is 6. Now we extend. Like before, we can deduce that if this graph were to hold the ratio, considering that it contains the previous graph, the additional paths must hold that same ratio with the structure within it. But here is where things get different. The additional paths must connect to at least one of the three new nodes on the right, and therefore can be divided into three groups. The paths that connects to the top right node, middle right node, and bottom right node. The amount of groups is correlated to the amount of layers. Here, we select the one that connects to the top right node, since that follows the structure's behavior. In other words, we have selected one-third of the additional paths. From here, we can use what we know from two-layer graphs. Half of the bottom two layers is the structure. Then, the structure of the additional paths looks like this. But this group was one-third of the additional paths. So, the structure here has 1/6 ratio with the additional paths, which means that the whole graph retains that ratio. Like two-layer graph, this reasoning can always be applied to the next iteration of the graph if the iteration before it holds the ratio, hence making every iteration thereafter true as long as we have a base case, an iteration that is proven to be true, which we have. So we have proven that the ratio, that being 6, between a three-layer graph and the structure will always be the same no matter the length of the graph. Now we go into four-layer graph. The structure in this base case looks like this and is 1/24th of the whole graph. Now we extend. Like before, we can deduce that if this graph were to hold the ratio, considering that it contains the previous graph, the additional paths must hold that same ratio with the structure within it. The additional paths must connect to at least one of the four new nodes on the right. Therefore, the additional paths can be divided into four groups. The amount of groups is correlated to the amount of layers. We choose the first one because it follows the structure's behavior. In other words, we have selected one-fourth of the additional paths. From here, we can use what we know from three-layer graphs. 1/6 of the bottom three layers is the structure. Then, the structure of the additional paths looks like this. But this group was one-fourth of the additional paths. So, the structure here has 1/24th ratio with the additional paths, which means that the whole graph retains that ratio. Like those previous graph, this reasoning can always be applied to the next iteration of the graph, if the iteration before it holds the ratio, hence making every iteration thereafter true, as long as we have a base case, an iteration that is proven to be true, which we have. So we have proven that the ratio, that being 24, between a four-layer graph and the structure will always be the same no matter the length of the graph. We can move on to five-layer graphs, but that will be repetitive. We can actually prove that the ratio between the structure and the graph is the same no matter the length for a n-layer graph by using previous reasonings for whatever n may be. We start with the base case, then prove that all next iterations retains the ratio by looking at the additional path ratio against the structure within it. This base case has a ratio of n factorial between the graph and the structure, because the structure is only one path out of n factorial many other paths. Now we extend the graph and observe that in order for this iteration to also hold the same ratio as the last iteration, the additional paths and the structure within it must also have the same ratio. The additional paths can be divided into groups, each group connecting to a specific node in the rightmost column. Since there's an amount of layers, the amount of groups corresponds to that. In other words, the amount of groups that we have corresponds to the amount of layers the graph has. We then select the graph that connects to the top rightmost node, which means that we have selected 1/nth of the additional paths. By using what we know from lower layer graphs, all the other layers below the second layer will still hold their own ratio, that being n minus 1 factorial. the structure looks like this. And since this group was 1/nth of all the additional paths, the ratio will still hold for the additional paths, and therefore so does the whole graph. Like all other examples we've done, this reasoning can be applied to the next iteration if the iteration before it satisfies this ratio condition. And since we have our base case to start it, that means every iteration thereafter also satisfies this ratio condition for n layer graph. This proof serves as a base template to prove individual graphs. So, how shall we go in proving all of them? Well, notice how in our proofs, the lower layer graph always helps prove the higher layer graph. If the lower one is true, so does the next one, and the next one, and so on and so on. This means for another proof by induction. If an n-layer graph satisfies our ratio condition for every single iteration, then the next graph, n plus 1 layer graph, will also satisfy the ratio condition for every single iteration. Because we have one layer graph to start it, every n layer graph thereafter will hold the ratio between itself and the structure within it, no matter the length, for whatever the ratio may be. There, proof done. But how does this correlate back to the binomial coefficient? And what's the ratio? The two-layer graph has 2 as ratio because there are 2 layers. The third layer has 6 as ratio because it has 3 layers, which stacks on top of the 2-layer graph below it. The fourth layer has 24 as ratio because it has 4 layers, which stacks on the layers below it. The fifth layer has 120 as ratio because it has 5 layers, which stacks on the layers below it. And the rest you can probably guess. So, back to this. Now we know that the structure is indeed the binomial coefficient we found in our formula. The numerator corresponds to every possible combinations in the graph, and the denominator corresponds to the amount of layers, factorial. The result becomes the structure, which corresponds to the amount of first terms inside the term or a sum of an arithmetic sequence. So, here are the formulas again, and thanks for watching.